Good morning. Uh, so there is a homework due this Friday. I the the due on Canvas yesterday was wrong, so I corrected it. But there is a homework due this Friday. Please just do the homework assignment. And uh, right, I will have an office hour today at 11 a.m. If you have questions about the lab or the homework, you can come and visit me. Right. So yesterday we talked about the alternating series test. We say that if we have an alternating series, test, it's a quick review of the test. So we say if we said if we have an alternating series, sum of an alternates, the sign of an, right? The sign of an alternates. Let's just do an alternates. Then in order to determine whether this series is convergent or not, we will look at its absolute value. We will consider the sequence Bn, which is defined to be the absolute value of An. And if Bn satisfies, Bn is decreasing, as well as the limits of Bn is equal to 0. If Bn satisfies both conditions, then An is convergent. The series An is convergent. And this is the alternating test. If the test fails, it doesn't mean the series is not convergent. It just means you need to find another way to determine whether it's convergent or divergent. Right. And right. So we were in the middle of this example. Right. So yesterday, before we ended, we were trying to figure out whether this series is convergent or divergent. So what we did is to let Bn to be the absolute value of the nth term in the series, which is n squared plus n cubed plus n squared divided by n cubed plus 1. And we have verified one of the conditions, that the limit of Bn is equal to 0. This is what we done yesterday. So today we're going to verify the other condition, whether Bn is decreasing or not. So is Bn decreasing? So according to the condition, what we want to show is that Bn plus 1 is less than or equal to Bn. And you can absolutely just do this. You plug in n plus 1, and you get the n plus 1 term is just n plus 1 squared divided by n plus 1 cube plus 1 less than or equal to n squared divided by n cubed plus 1. So you can absolutely do this, and then you try to simplify it. But as you can see, the simplification will take a lot of time, because there is an n plus 1 cube term here, and there's an n plus 1 square term here, and you need to multiply both sides by the products of the denominators. Then you have to simplify all the, well, let's just put it in this way. It takes a lot of time. And what you can do, what other things you can do to show Bn is decreasing here is that you just, this is one way. is another way, is that we call that Bn as a sequence. We can consider it the corresponding function of it, which means you consider the f of x where you replace all the n with the s x. So you get this equal to x squared divided by x cubed plus 1. And then you just need to show this function is decreasing. So you will take the derivative of it, f prime of x is equal to x cubed plus 1 squared. Then you get 2x multiplied by x cubed plus 1 minus x squared times 2x squared plus 1. And then this is equal to 2x minus x squared. What is that? 2x x squared. Right, oh, yeah. This is, my bad. This is 3x squared. Okay. Right, so then after you do simplification, you get this is equal to 2x minus, it's not x squared anymore. This is 4x cubed. Let me make sure, sorry. Right, just x cubed. Okay. Yeah, and then this is the x cubed plus 1 square. And since we want to show this guy, show the sequence is decreasing, so we want to show f prime of x is less than or equal to 0, at least from some finite number. And in order to do that, we need to find where f prime of x is equal to 0. So you let f prime of x be 0, you get x is equal to 0, or x is equal to square root of 2. Just need to solve this equation where you get 2x minus x cubed is equal to 0, or x is equal to negative square root of 2. Yeah. Then from here, you get, so you can try to grab it, or you can, well, you can try to plug in some number. You can see when x is greater than square root of 2, the f prime of x is less than 0. Wait a second. Let me make sure this 2x. No, this is x to the 4. Right. This is x to the 4. I made a lot of small mistakes. So if you ever find one, just let me know. So this is x to the 4, and we need to change this accordingly. It's x to the 4. So this is cubic roots of 2. And this is cubic roots of 2. But this is something you can verify. And we only care about all the term that's greater than or equal. We only care about when n is large. Care about the case when n is large, because we know that finite number of terms doesn't change the convergence and divergence of or divergence of the series. So in this case here, when x is greater than cubic roots of 2, f prime of x is greater than 0, which means when n is greater than cubic roots of 2, which is less than 2. So when n is greater than or equal to 2, the n is decreasing. And we don't care about B1. It doesn't matter. As long as Bn start decreasing after a finite number, then we can still use the alternating series test. And now from this and the condition we have verified last time, the limits of Bn is equal to 0. So from the alternating series test, this series, -1 to the n plus 1 power multiplied by n squared divided by n cubed plus 1 is convergent. Any questions? Okay. The key points of this example is that you don't have to the decreasing of Bn doesn't have to start from n is equal to 1. It can start from any finite number. As long as it keeps decreasing after that finite number, you can always use the alternating series test, which is similar to what I have mentioned for the comparison test and the integral test. But you don't have to use alternating series test for every alternating series. And alternating series that test does not always work for an alternating series. For example, if you want to calculate, if you want to determine whether this series, -1 to the n power times 3n divided by 4n minus 1 convergence, whether this series is convergent or not. Then if you try to use the alternating series test, if we use the alternating series test, then the procedure is we let Bn be the absolute value of the n term in this series, which is 3n divided by 4n minus 1. And when you calculate the limits, you realize the limits of Bn, n goes to infinity, is equal to 3/4 and is not equal to 0. So this case is when the alternating series test fails. But even the alternating test failed, we still don't know whether this series is convergence or divergence just from the test, because this is a test that can only tells you whether the series convergence when it's actually convergence. When series is divergent, you get no information from this test. So right, test. So you can't determine, you cannot determine whether it's convergence or not. It converges or not from the alternating test. So you have to find some other way to determine this series. So for this example, because we have calculated the limits of Bn is not equal to 0, you can easily imagine that An is just some number. It's just either -1 or +1 of Bn. So if you compute the limits of An as n approaches infinity, right? Here by An, I refer to the term in the original series, the nth term in the series 3n is 4n minus 1. And then if you calculate these limits, you realize this limit does not exist because the absolute value of the limits of the absolute value of this series is 3/4, but it's bouncing between 3/4 and -3/4 since because of the -1 to the n power there. So when you take the limits, the behavior you will see when n is larger n. The behavior you will see from this series is that it's bouncing between -3/4 and 3/4. So the limits of this sequence doesn't exist. So so from the test for divergence, the test for divergence is that if the limits of the term in the series is not equal to 0, then the series is divergent. So in this case, the limits doesn't exist. So it's definitely not 0. And from the test for divergence, the series -1 to the n power 3n divided by 4n minus 1 diverges. Any questions or comments? Okay, let's introduce another kind of convergence, which is stronger than the convergence we have learned. So now, this is the absolute convergence, or convergence. This is a stronger type of convergence. The series An is called absolute convergence. Convergence. If the series of the absolute value of the original series is convergent, and there is an immediate theorem for the absolute convergence. If a series of An is absolute convergence, then it is convergent. So it's this absolute convergence is a sufficient condition to the convergence. And if a series is not absolute convergence, it doesn't mean the series is not convergent. We will see two examples really. in a minute. So the first example I'm going to show you is that the alternating series, but the absolute value of it is the harmonic series. So this series, I think it's example 4. This series is convergence. Series is convergence. Because if we let Bn be its absolute value, which is 1 over n, we can show that Bn is decreasing, and the limits of Bn is equal to 0. So from these two conditions and the alternating series test, we get the original series -1 to the n power 1 over n multiplied by 1 over n as convergence. But the series, the absolute value of -1 to the n power times 1 over n is equal to the series 1 over n. So it's divergent. And this is an example that the series is convergence, but not absolute convergence, or absolutely convergence. And then as a comparison, let's consider this example, -1 to the sum of -1 to the n minus 1 power multiplied by 1 over n squared. So now this series, if you take the absolute value, and consider the series of its absolute values, this is equal to the sum of 1 over n squared, and this is convergence. So from the P series test, or the P series, the theorem of P series with P equals 2. So it's convergence, which means this series is absolute convergence. Square is absolute convergence. Absolutely convergence. And thus it's convergence from the theorem. And use the absolute convergence test or the absolute convergence theorem. Sometimes you don't have to use the alternating series test to determine it. The limits of it is equal to 0, and the absolute sequence is decreasing. and well, you can say some time. But the introduction of the absolute convergence, it's mainly for the next test we're going to learn, which is called the ratio test. Let's see, right. And the ratio test will be the test we will use the most in the rest of this chapter. Right. So the ratio test, suppose we have a series AN if right. Now we let L be the limits of the ratio between two adjacent terms, AN plus 1 divided by AN, the absolute value of the ratio as n approaches infinity. And the ratio test tells you that if L is less than 1, then AN is absolutely convergent. And because it's absolutely convergent, so it's also convergent. And if this ratio is greater than 1, AN is divergent. And if this ratio is equal to 1, the test fails. And AN is inconclusive, which means you can't get you can't get the convergence or divergence of the series from the test, from the ratio test. You have to use some other test. This will be the primary test we use for the following sections in this chapter, where we will introduce the power series. So there are two notes I want to put here. So the ratio test, you can consider it as a comparison with the geometric series, because the limits, the L is determined to be the limits between the two terms, the ratio, the limits of the ratio between the two terms. So when n is sufficiently large, AN plus 1 is approximately L times AN. Or I should do this first. So the ratio between them, AN plus 1, the absolute value of AN plus 1 and AN is approximately L. And this implies AN plus 1 is approximately L times AN. So intuitively, you can think of the series starting from certain terms, starting from a certain term. The series acts like or behaves like the series. The absolute value of AN behaves like a geometric series. Because the ratio the ratio between two adjacent terms is approximately a constant. So the series somehow looks like a geometric series when n is sufficiently large. And for the geometric series, we know that when the ratio L is greater than 1, the series divergence yeah, the series here I meant is the absolute value of an, and when L is less than 1, this is convergence. And right. And so this an, the original an is divergence. But when L is large, is greater than 1, you can expect when n goes to infinity, the term an is not a 0. And from the test for divergence, you can get divergence. But when L is less than 1, you get the series of the absolute value of an is convergence, which means the original series an is absolute convergence. So it's that original series is also convergence. But when L is equal to 1, we can extract or get any information from the ratio test. And we can see that from an example. When n is equal to 1, the series can, when L is equal to 1, the series can either be convergence or divergence. For example, if we consider the series 1 over n, and if you calculate the limits as n approaches infinity of the two adjacent terms, you get 1 over n plus 1 divided by 1 over n, which is the limits as n approaches infinity of n divided by n plus 1. And this is equal to 1. But this series is a p series with p is equal to 1, or you can call it a harmonic series. This is a divergent series. And as a comparison, we can consider 1 over n squared. Again, we calculate the limits, n goes to infinity, 1 over n plus 1 squared divided by 1 over n squared. This is equal to the limits as n approaches infinity of n squared divided by n plus 1 squared. And this is also equal to 1. You can check it yourself. But this series is convergent. So when the ratio is equal to 1, you get the series can either be divergence or convergence. So no information or no conclusion we can draw from the ratio test. The test fails. We need to try some other test. Any questions or comments? All right, so let's see an example. Let's consider this series, -1 to the n power times n cubed divided by 3 to the n power. So for this example, let's apply the ratio test. Here's the ratio test. So we have an is equal to -1 to the n power divided multiplied by n cubed plus 3 to the n power. an plus 1 is just replace all the n with n plus 1. So this is negative 1 to the n plus 1 power. This is the n plus 1 cube divided by 3 to the n plus 1. And in order to use the ratio test, we need to compute the ratio, the absolute value of the ratio. Which gives you so negative 1 to the n plus 1 power times n plus 1 cube divided by 3 to the n plus 1. Then the whole thing divided by negative 1 to the n power times n cube divided by 3n. Then now we need to simplify this ratio. Because we have an absolute value, the negative 1, the negative 1 makes no difference here. We can just drop them. And you get n plus 1 cube divided by 3 to the n plus 1. And then the whole thing divided by n cube, the ratio between n cube and 3 to the n power. And this is equal to n plus 1 to n plus 1 cube divided by 3 to the n plus 1 times 3 to the n divided by n cube. And we can do some simplification here. This 3 to the n power cancel the bottom at the denominator. The 3 to the n plus 1 power in the denominator, and you get a 3. And there's nothing we can cancel for these two terms. So you get, in the end, the ratio is 1/3 times n plus 1 divided by n to the cube. And this is the ratio. We want to take the limits of this ratio. So when n goes to infinity, the limits of an divide the limits between of the ratio between an plus 1 and an is equal to the limits as n approaches infinity of 1/3 times n plus 1 divided by n cube. And this is equal to 1/3, because when it goes to infinity, this term, the second term, goes to 1. So the limits of the ratio is equal to 1/3 and is less than 1 from the ratio test. The series, negative 1 to the n power times n cube divided by 3 to the n power is convergent, or absolutely convergent.
Does it matter how we write the answer? Like, does it have to be absolutely convergent, or can we just put convergent?
Convergent is enough because we are looking, because we are studying whether it's convergent or not. But well, yeah, it doesn't matter. You can just write convergent. Any other questions or comments? As you can see from this example, the ratio test is very useful when we have a term like something to the n power, because the next term will have a n plus 1 power, and then you can cancel the terms. You can simplify it by cancel the common factor when you compute the ratio, which will be the case in the power series.
You tried using the alternate series test on this one first, or was that one not possible for some reason?
I think alternating series test for this one. I think alternating series test should still works for this one, but it's much more complicated.
Oh, okay.
Yeah, if you are using alternating series, you have bn is equal to, let's see, n cubed divided by 3n. And then you want to show this, the limits of this bn is equal to 0, which I believe you can do x cubed divided by 3x and use the L'Hopital's rule, but you have to use it like 3 times for these questions.
But you
then-
can't get absolute convergence out of the absolute value or the absolute test, right? So would it be not the full correct answer because it'd only be convergence and not absolute convergence?
Well, this series itself will still be convergent. How can I show this convergent? But I'm not sure if I can show this as convergent. You can probably, for this series, you can probably use the integral test, but it will. But as I mentioned, this will be very complicated because you have to integrate this dx.
Okay.
So if you choose any other tests we have learned for this series, it will be much more complicated than the ratio test. That's
Okay.
the point I want to make here.
Okay, thank you. That sounds good. Thank you.
So usually if in the future you see there is a power term, like in this case, there's 3 to the n power terms in the series, you may want to try the ratio test first. Because when you have a power terms, for example, you have, in this case, let me use another example. For example, if you have the sum of n times e to the negative n, if you use the ratio test because there is an e to the some power here, the next term, if you the nth term, so this is a new example. The n term is n times e to the negative n. The n plus 1 term is n plus 1 times e to the negative n plus 1. And when you compute the ratio, n plus 1 divided by an, n plus 1 divided by e to the negative n plus 1, and n times e to the negative n, you will see that this e to the negative n can be cancelled. And it can simplify this expression a lot. Like this, n plus 1 divided by n times e to the negative n. So if in the future you see a power term like this, or maybe 3 to the n power in the series, you may want to try the ratio test first. Okay, let's do one more example today. Now let's consider another example. Let's consider this series, n to the n power divided by n factorial. So again, this n is on the power. We can try the ratio test. The ratio test. Have an plus 1 divided by an, take the absolute value, get this is equal to n plus 1 to the n plus 1 and n plus 1 factorial divided by n to the n over n factorial. And right, the factorial, n factorial, in case you forgot it, in case you have forgotten it, is equal to the products of 1, 2, 3, all the way to n. So it's the products of the first n integers, positive integers. So so then n plus 1 factorial is just equal to n factorial times n plus 1, because this is the products of the first n integers, and this is the products of the first n plus 1 positive integers. So the difference between them is just the n plus 1. And then from here, you get this is equal to n plus 1 to the n plus 1 power divided by n plus 1 factorial times n factorial divided by n to the n power. And this thing, this whole expression, is equal to n plus 1 times n plus 1 to the n, which I just factor out a n plus 1 from the n plus 1 to the n plus 1 power divided by n plus 1 factorial times n factorial divided by n to the n power. And because n plus 1 factorial is equal to n factorial times n plus 1, so the products of this term, n plus 1, and the n factorial is equal to n plus 1 factorial. So it can cancel the n plus 1 factorial in the denominator, which gives you n plus 1 to the n divided by n to the n times n plus 1 times n factorial divided by n plus 1 factorial. So these two cancel. And what is left is n plus 1 to the n divided by n to the n. And then we can do some simplification here. This is equal to, we can combine the two n power term, get n plus 1 divided by n, the whole thing to the n power. And this is equal to 1 plus 1 over n to the n power. And now when you take the limits, this guy goes to e. This is from the definition of this limits, or yeah, I think e is defined to be the limits of this thing. 1 plus 1 over n goes to infinity is equal to e. I think in engineering Cal 1, the limits we have seen is the limits of x approaches 0 of 1 plus x to the 1 over x is equal to e. In this case here, when n goes to infinity, you can let x be 1 over n. So then when x goes to 0, n goes to infinity. Or I can add 0 plus here, which represent x as a positive number. And if we let x is equal to 1 over n, when x goes to 0 plus, n goes to infinity. And this limits becomes the limits as n approaches infinity of 1 plus 1 over n, because x is equal to 1 over n. 1 over x is, is n. This is equal to e. So they are equivalents. And the limits of this expression is e when n approaches infinity. And e is a number that is greater than 1. So the ratio is greater than 1. Then from the ratio test, the series an diverges. It diverges. Any questions or comments? Okay, we will meet on Friday. If you have any questions, you can drop by my office hour, which will be 11 a.m. this morning. So see you guys later.
Thank you.